Now we are going to discuss about a case study on Poisson distribution. Introduction. Poisson distribution, which was developed by Simon Danius in 1837, is one of the three discrete distributions such as binomial, hypergeometric and Poisson that uses integers as random variable. The Poisson equation for predicting the probability of a specific number of defects or failures in time is given as follows. P of r is equal to lambda t the whole power r into e power minus lambda t divided by r factorial, where r is equal to number of failures in time t, lambda is equal to failure rate per hour, t is equal to time expressed in hours. P of r is equal to probability of getting exactly or failures in time t. In order to determine the probability of k or fewer failures occurring during time interval ti, the probability of each failures occurring during the same time interval must be calculated. The probability of k or fewer failures occurring can be given as follows. P of r less than or equal to k, which is equal to summation r is equal to 0 to k P of r. The confidence level that population has a failure rate lambda based on r less than or equal to k failures occurring during time interval t is CL is equal to 1 minus P of r less than or equal to k. Now we are going to discuss about the case study. In this study, the Poisson distribution is used in predicting the failures of components in power system. In order to evaluate the validation of the study of the statistical maintenance or repair data from the state utility company of Adiyaman district was used. The results show that the Poisson distribution can be used to schedule the preventive maintenance and improvement of power system reliability purposes. Analysis. In this part, the data provided by the state utility company of Adiyaman district is related to the failure of fuses and transformers. The failure of each fuses and our transformer is assumed to be independent of each other. It means that the failure of each transformer does not initiate the failure of another transformer in the same supply line. The failure of a transformer may affect the supply of another one in the same supply line, but this does not mean that it will initiate the failure of the other transformer. In some special cases, the failure of several or more transformers may affect each other, but these cases are not included in this study. It is also assumed that each transformer failure is repaired or the transformer itself is replaced immediately. This is a fairly valid assumption in the repair or replacement time is much shorter than the time to failure. Therefore, instant repair for each transformer is assumed. There are 1,394 transformers installed in the combined medium voltage and low voltage level of power system of the city of Adiyaman. On the average, there are 43 transformer failure per year based on the collected data from 2001 to 2004. A sample of data collection sheet is given below. The failure rate of the transformer is 37 transformer per 8,760 hours. The calculation and analysis are carried out first for a time period of 1 year, then for a time period of 5 years. This is our collected data collection sheet. Next, results. The probability density function for the transformer is calculated by employing a failure rate of 43 transformer per 8,760 hours in the Poisson equation. The probability density function is given in the following figure 1. This calculation is carried out for 1 year. The vertical axis shows the probability of failures while the horizontal axis shows n number of failures. It is obvious from the figure that the probability of getting exactly 43 failures in 1 year is the highest, which indicates that most probably there would be on the average 43 failure in a year. This figure indicates the probability density function of transformer failures. X-axis nothing but number of failures in 1 year. Then corresponding y-axis is nothing but probability of failure. The probability distribution function for a period of 1 year was also calculated using the equation 2. The results of the probability distribution function are presented in figure 2. The x-axis indicates the probability of occurrence of n failure or less, while y-axis shows the probability. As expected, the figure shows that the probability of getting 43 transformer or less is about 1, which is in agreement with the data. Then the confidence level of transformer failure for a period of 1 year was calculated using the equation 3. The results are given in the following figure 3. Here x-axis denotes the number of failures in 1 year. The y-axis denotes the confidence level of the transformer. The figure shows the confidence level of getting, for example, 20 failures is 1, which is expected is 1. Since the failure rate of transformer is 43, in other words, we are statistically 100% sure that there will be 20 failures in 1 year. The confidence level of getting 40 failures is around 10%, which is agreement with the data. The probability density function of transformer failure is now calculated for a period of 5 years, and the results are presented in a 3D graphs given in the following figures. The x-axis shows the time in with steps of 6 months. 10 is equivalent to 5 years. The y-axis indicates the number of transformer failures, while the z-axis shows the probability of failures of exactly n failures. This figure indicates the probability density function of transformer failures in 3D. Figure 5 indicates the probability distribution function of the transformer failures in 3D. Figure 6, the confidence level of transformer failure in 3D. Conclusion. The Poisson distribution function was used to predict the transformer failures in the grid of power system of the state utility of Company of Adiyaman district. The probability density function, probability distribution function and the confidence level of transformer failures were first calculated for a period of 1 year. The calculations were carried out for a period of 5 years. The results were presented in 2D and 3D graphs using MATLAB simulation tool. Thank you.